this chapter 9 out of the way. Okay, so we were doing the buffers, and of course, here's one of the buffer problems. And you'd find the buffer system in the appendix. You always have to look it up by what? It's a table of KAs, so you have to look it up as an acid, right? And so it'll always be the conjugate acid you have to look up. And then by definition, that buffer would then, well, that acid would disassociate on that table, right? That's what you're looking up. Okay, we looked that up for hypochlorous acid. pK is that number right there. The pH is known in this problem. That's actually what you're given, is the pH of this buffer system. So what we need to figure out is we're going to get the ratio of base to acid, right? And we're going to use the Henderson-Hasselbalch equation. I think you've all taken biochemistry, so you all know this really well. Ironically, biochemistry is where you really master the Henderson-Hasselbalch, right? It becomes a part of you. By the way, if you want to flip these ever, you just need to change the sign of the log. You know that, right? You can flip these. Just change sign of log. So if you ever want the ratio the other way around, just flip it and change the sign. Okay, anyways, that's that. Do you have any questions? No? Yeah, honestly, you've done it plenty of times before, right? If anybody has any questions, always please just ask. The conjugate base for weak acid is going to be a weak base, of course. The weaker the acid, the stronger the base. If you get something that's a strong base or strong acid, that means its conjugate base, conjugate acid are so weak they have no basic or acidic properties, right? Strong acid, Cl- has no basic properties. So if one member of a conjugate pair is weak, it has to be able to have a conjugate that would also then be a weak acid or weak base. The relationship between the Ka for an acid and Kb is, of course, always through Kw. You always take Kw and divide it by the other one, because it's Kw equals Ka times Kb. Shit, I got this from your book and it's wrong again. I really need to go through here and very carefully, anybody notice what's wrong here? The Kw and Ka are switched. Oops. I don't know. All the figures I get from your guys' book are always weird. Whatever. The figures in the book are right. All the stuff in the book is right. It's still good, but they just make my life hard. All right. So when a strong acid or strong base is added to a weak acid or weak base, they're going to react essentially completely. Okay? It'll be very nearly completely. Of course, nothing ever reacts completely, but this is going to be as close as you're going to get. So what does that mean? Well, when you add a strong acid to a weak base, like this problem right here, you essentially just use up the weak base, right? And convert it to its conjugate acid. Does that make sense? And you've done this before. Do you have any questions about how to do this? So essentially you do like a little mini ice problem, right? Where you've used up the base and you've converted it to the conjugate acid, which is what you're doing right here. And then you would do the Henderson-Hasselbalch, right? Unless you use up all the base. In which case, no Henderson-Hasselbalch. Because you've used it up all of it, right? Okay. All right. And then the same thing with an acid. If you add OH minus, you're going to start with some of the OH minus, right? And again, that's going to use up some of your weak, your conjugate acid, if you start with an OH minus being added. Do you have any questions about that problem? I'm just going to skip over it if you don't. Again, if you want to see how much pH is going to change by adding an acid or a base, you would again just subtract that off of one side, and that would get added to the other, right? Which is, again, basic problems you've done back in Gen Chem 2, and you did again in biochemistry if you took that before this one, which you guys did. So the pH of a buffer is going to be nearly independent of dilution. Your pH is a factor of how much acid to base you have, right? And because both of those solutions are in the same solution, you always have the same volume, don't you? Did you realize that? Concentration of the conjugate base over the acid. Well, they both have the same volume, so they'll cancel their volumes, won't they? Okay. So you can put mole over mole ratio. That's fine, because they're in the same solution. However, the dilution of a buffer is going to change its buffer capacity. So that's going to be a measurement of the concentration of your buffer. As you increase the concentration of your buffer solution, the buffer capacity increases. How much acid you can add without changing the pH significantly increases as concentration of your buffer increases, right? What happens if you decrease the concentration of your buffer? Can you add as much acid before it changes pH significantly? No? Yes? Okay, so what's buffer capacity? You guys remember that? It's the amount of an acid or base you can add before it significantly changes the pH. Why do I keep saying significantly? Yeah, it always changes the pH a little, right? But buffers keep it from changing significantly. Okay. So the buffer capacity, if I decrease the concentration of my buffer, what's going to happen to my buffer capacity? It's going to change it. It's going to decrease it, right? If I increase the concentration, it's going to increase it. Okay. Think of this like a balance, or like one of those. What is that plank of wood that kids put their weight on? What is that called? Do you guys remember? No? Nobody played as a kid? Good God. Okay, there's a piece of wood with a little thing in the middle, and then kids go on it and seesaw. Thank you. Damn. I was having a memory blank. Yeah. Everybody had a memory blank. Yeah, I couldn't remember seesaw, honestly. It's just one of those days. So buffer capacity is a bit like a seesaw. So the buffer, the pH of the buffer is going to be how it's balanced, right? And that depends on the two kids on it, doesn't it? Okay? The weight on each side. The buffer capacity would be like how long that seesaw is. If that seesaw is long enough, it's not going to matter if you put like a grain of sand on it, right? That's not going to change how it's balanced, is it? Do you see that? Okay. So buffer capacity is dependent on concentration, the amount of buffers there. The pH of it has absolutely no relationship to the amount of buffer. That's just the ratio of the base to acid. Okay? Okay. So you must have more moles of buffer present than there are moles of acid or base that could be introduced into your solution. If you do not, then you will overwhelm your buffer system, destroy it, and it will change pH rapidly. Okay? It'll react it all the way. The maximum buffer capacity for a solution is going to be at pH equals pKa. Why is that? Okay, so what if I have a something that the pH is like several units higher than the pKa? What does that mean? Well, that means I have almost no buffer capacity on one side of that, right? I've essentially used my buffer up on one side. Okay? And that means it's not a useful buffer, is it? Because if I put a single drop of, let's say my pH is higher than my pKa, if I put a single more drop of base, it's going to shoot up a unit of pH, isn't it? It won't matter. I won't have a useful buffer, will I? So that's the ideal, the maximum buffer capacity. The useful range of a buffer will be 1 unit of pH around the pKa. So the pKa plus or minus 1. And again, that's because pH equals pKa plus log of the ratio, right? So once you get past 1 above or 1 below, you're talking about 100 to 1, 1,000 to 1 ratios, right? Meaning you have almost nothing on one side of it. You've used it all up on one side. So this is how you choose a buffer system. If you want a buffer system that works at pH 3.6, what should the pKa be? You want pH to equal pKa, right? Or as close as you can get. You need it to be within plus or minus 1, right? Okay. So you're always going to look at your exponent of the Ka value, unless you're given pKs, of course, in which case you can just look at the number, right? It should be close to the pH desired. So again, what weak acid would be appropriate for making a pH 10 buffer? Could I use acetic acid and just add base until it gets to pH 10? No, I would have used up all my buffer, right? That'd be useless. So what weak acid would be there near there? Well, something like ammonia, right? Something that's normally a weak base, and we've acidified it. So ammonia, NH4, has a Ka of 10 to the negative 10, right? So it's very close to where our buffer should be. That would be appropriate. Its pK is actually 9.24 if you're curious, which is the number you actually want to use. That's within the plus or minus 1 range, though it is a little bit on the further side of that. Like there are bases that could theoretically be better buffers, but many of them actually would be more problematic to use. So ammonia is a good one because it's cheap, easy to get. And it would work well here, right? Anybody know how you would make this buffer system? No? Okay, you could use like ammonium chloride with a little bit of ammonia, which is NH4OH, right? You can mix those together, ammonium chloride and ammonium hydroxide. Like a 50-50 ratio would do it. 1 mole to 1 mole ratio, right? The other way you could go about it is you could take one of them, like ammonium hydroxide, and then you could put acid in there until you neutralize a portion of it, like half of it. Okay? Or you could take ammonium chloride and put base in there until you neutralize half of it, right? All right. But again, don't forget, if you make it, you have to put in essentially double what you would have needed to put in. Here's what I'm saying, because you're neutralizing half of it. Don't forget to take that into account. By the way, that's one of the most common jobs in industry.